LeChatelier's principle. LeChatelier's principle states that if a system is at equilibrium, and that equilibrium is stressed by any one of a number of disturbances, for example, a change in temperature, or a change in pressure, or a change in concentration of one of the components, or more than one of the components, then the system is going to shift to relieve that stress, or in such a way as to counteract the effects of that stress. So this reaction is a great example of a reversible process, and it's called the Haber process, in which ammonia is produced. Now, in the Haber process, all of the components are gases. So nitrogen, hydrogen, and ammonia are all in their gaseous form. If we were, say, to disturb the equilibrium that forms in this process by adding more nitrogen, then, well, that's more stuff in the road. Equilibrium is going to shift in such a way as to remove that additional reactant. And it's going to remove that reactant by forming more product. So, anytime you add to the reactant side, if you're adding something that is a gaseous substance or an aqueous substance, then equilibrium is going to shift to remove that reactant by forming more product. If we were to remove that nitrogen gas, then equilibrium is going to want to shift in the direction to replace it. So by removing something that's on the reactant side, equilibrium is then going to shift to replace it. So we would say that equilibrium is going to shift to form more of the reactant. Now let's take a look at what happens to equilibrium if we remove ammonia. So now I'm removing from the product side. Equilibrium is going to want to shift to replace the ammonia that I have removed. So equilibrium is going to shift towards producing more ammonia. Now, equilibrium is also affected by changes in pressure. And in this example, we're showing the three gases involved in the Haber process. On this side, we have one molecule of nitrogen and 3 molecules of hydrogen. And then what happens is we decrease the volume that container will allow. And when we decrease the volume, what ends up happening is we increase the pressure on the gases. Now, an increase in pressure on a system of equilibrium amongst gases is going to cause a shift to relieve that increase in pressure. Now, notice that on the reactant side of this equilibrium, we have 1 molecule of nitrogen and 3 molecules of hydrogen, or 1 mole of nitrogen and 3 moles of nitrogen. Okay? But that's a total of 4 molecules on the reactant side. On the product side, we have 2 ammonia molecules, or 2 moles of ammonia molecules. So, in the event of an increase in pressure, in this case caused by a decrease in volume, the equilibrium is going to shift to relieve that increase in pressure. That means it's going to shift in whatever direction is going to give the molecules more space. It's going to take up less space. So, since we're going from 4 molecules on the reactant side to 2 molecules on the product side, by increasing the pressure, we would cause the equilibrium to shift toward the formation of more products. That way, those ammonia molecules will take up less space than what's over here on the reactant side. Here's another reaction showing the dissolution of solid sodium hydroxide in water, forming sodium and hydroxide ions. Now, in this particular reaction, we would show sodium hydroxide as a solid. And of course, water is a pure liquid, and ions are aqueous. Now, if this system is at equilibrium and we decide to stress the system by, say, removing some hydroxide ions, in that case, equilibrium is going to shift to replace them or towards formation of more product. But what if we decided to add more sodium hydroxide? Well, sodium hydroxide is a solid, and since it's a solid, even if the mass of the sodium hydroxide decreases, the volume is going to decrease by a proportional amount. Its density will not change. And since density is mass over volume, and molarity is moles per liter, and we know that the density of the sodium hydroxide is not going to change, then we would consider that the concentration of the sodium hydroxide is not going to change either, as long as there's some present to react. And so, addition or removal of sodium hydroxide, since it's a pure solid, is not going to have any effect on equilibrium. So equilibrium would not change in the event that we added a solid. The same is true if we add or remove water, which is a pure liquid. Okay? Pure solids and pure liquids do not change the equilibrium of a system. And if we were going to write an equilibrium expression for this reaction, we would simply leave them out using the formula or the expression K is equal to the concentration of sodium ions times the hydroxide ion concentration. Remember our generic equation A plus B yields C plus D. If we write the equilibrium expression for that, then this is what we get. And if we're to affect equilibrium by, for example, adding more product and shifting equilibrium toward the formation of more reactant, then C and D are going to react to produce more A and B. So the concentrations of A and B will end up increasing. The concentrations of C and D ultimately will decrease as they form more reactant. And so the value for K stays the same. There's only one thing that's going to change the value of the equilibrium constant, and that is temperature. Consider this reaction. We're given a delta H for this process of a positive 87.9 kilojoules. Now I know that if I have a positive delta H, that means that this is an endothermic reaction, which means that heat needs to go into the system for this reaction to move in the forward direction, or I could just look at it as heat is a reactant, and then just treat it as any reactant. In other words, if I add heat, then equilibrium is going to shift toward the formation of products because it's an endothermic reaction. Heat is the only thing, though, that will actually change the value of K in an equilibrium reaction. Now for this reaction, delta H is less than 0. If delta H were a negative value, then that would mean that this was an exothermic process, meaning heat were given off from the process. So again, now I would consider heat to be a product, since heat is given off in the reaction. And then if heat were added to the system, just as adding any product to the system would cause the equilibrium to shift in the direction of formation of reactants. Just remember, the only thing that can change the value of K is heat.